All right, folks, I apologize. This is highly unusual. We're Smileys are having a rough time of it. So here's lesson 3, kinematic equations. So in this lesson, you'll be able to determine when and when not to use velocity is equal to displacement over time, determine which kinematic equation to use, and how to solve problems that involve constant acceleration. All right, so I posed you this experiment. We've got a ball is going to roll down this ramp here. And this ramp is 1.2 meters long. So we have 1.2 meters. And we're going to time that, measure this on your marks. Get set. Wait for it. Go. Okay. That was 1.6 seconds to go down there. Did the ball experience acceleration? Well, yeah. I mean, it started at rest and then it wasn't at rest, so it had to have changed. Actually, was speeding up the entire time. So, how could we solve for this final velocity? So, what I want to know is how fast is it going right here when the ball was like right at the end? How fast was that ball moving right at that location? Okay. So, could we use? We've got displacement and time. So I'm like, hey, you know what? We could displacement and time. I'm looking for velocity. I mean, shoot, I've got all the numbers. But what does this give me? This gives me my average velocity, not my actual velocity. So as this was going, it's going to give me my average velocity. Well, this started at rest here, and now it's moving here, and it's speeding up the entire time. What it's going to give me is your average velocity during that whole period of time. And so I don't know exactly how fast it's going at the end, and that's the problem with that. So this breaks down only finds the average. So if velocity is changing, this only finds the average velocity and not the actual, okay, which I want. So if I were to graph this motion of the bowling ball as it rolls down the ramp, it's gonna speed up in the positive. We're gonna say down the ramp is positive. It's gonna speed up in the positive direction. So if we were to use this equation, what that's gonna do is that's gonna give me the slope of the line from there to there, which, you know, it's a good approximation, but really what I want to know is I want to know how fast is it going right there. So I'm like, what can we do to get a better approximation? Like we've got this data, and what I could do is I could make a smaller segment of time. So I could do this. Okay, that's getting closer, right? So what could I do to get even closer still? Maybe if I like go in here and do from these 2 points like a tenth of a second, I could get that better. But really, we're still doing an approximation. It's getting better, and this is what calculus gets at. But we're not in calculus, so here's how we're going to solve this problem. They've used calculus and they've come up with these 4 kinematic equations. Now, on the onset, this is like really intimidating, but I want you to look through and find a variable that you've not seen before. The reality is you've seen them all before. They're just rearranged in different ways. So we can use these kinematic equations anytime there's acceleration. Okay, so I'm going to coach you on how to use them, but these now are four. So you had two equations in your toolbox. Velocity is equal to displacement over time, and then acceleration is equal to change in velocity over time. Now you've got these four. So kinematic equations, when should you use them? When velocity is changing. So if you are able to discern, oh yeah, velocity is changing, kinematic equations specifically when there's acceleration. You can use those. You should not use this equation. Velocity is equal to displacement over time when velocity is changing. And when can you use this equation? Velocity is equal to displacement of time when velocity is constant. Because then the average is your actual and you're good to go. Okay? So if velocity is changing, stay away from that equation. Okay? So, example, a child slides down on a toboggan with an acceleration of 1.5 meters per second squared. If she starts from rest, how far she traveled in the first 3 seconds. So, step one, excuse me, we're going to draw a hill and the kid on a toboggan, just draw a square, easy. I'm going to pick your initial and final position. So we're going to be up top at rest. That's my initial. Final is when she's at the, how far she traveled in 3 seconds. So she doesn't necessarily have to be at the bottom. So 3 seconds later. And make the way, if the positive direction is not defined, make the way it's moving positive. So I'm going to make down the ramp positive. And now I'm going to set up, I'm going to start defining my variables. Okay, so the best way to do this is to look at your units. Your units are your name tags. Okay, so it's like, hey, 1.5 meters per second squared. Nice to meet you. I'm acceleration because it's in meters per second squared. Hey, 3 seconds. What's up? So seconds, that's the unit. Oh, that's a measure of time. Okay, so we're defining those things. So we've got acceleration is positive 1.5 meters per second squared because we're speeding up in the positive direction. We have a time of 3 seconds. So those are all our numbers. I need one more because I need 3 things defined to be able to use these kinematic equations. I need one other thing from the problem. I need some other variable given a value. So can you find it? Pause it. Pause the video. So she starts from rest. That tells us our initial velocity is equal to 0. Starts from rest. If you start from rest or if you end at rest, your final velocity is 0. So here, initial velocity is equal to 0. So sometimes you have to read the context of the problem. And how far, so that is delta x. I'm looking for that. So those are, I've got 3 values identified, and the 4th one I'm looking for. So now, only now do we go shopping for which equation should I use. So the way you do that is you look to see, all right, which equation has those 4 things. Okay. So go ahead and pause the video and see if you can figure out which equation you're going to use as all 4 of those variables. Okay, so going through here just to make things good. Okay, so this one we don't have This is an unknown final velocity, and I've got this, this, and this. So it has one unknown, but that unknown that I am solving for, I don't care about. So I'm not going to use that one. Displacement. Oh, that's what I'm looking for. Initial velocity, yeah, I got that. Final velocity, I don't know. Time, I've got. So here I've got two unknowns. So that's a no-go. Displacement, I'm looking for. Initial velocity, yes, I have. Time, I have. Acceleration, I have. Time. Oh, and this is the one that I don't know, and I'm looking for it. Ding, ding, ding. That's our winner. So I'm going to write that equation out before I use it. Okay. Just for complete sake, final velocity, looking at this last equation, final velocity, I don't know. Initial velocity, I have. Acceleration, I have. Displacement, I don't know. I've got two unknowns, so that's why that one's out. Okay. So, excuse me. All right. So I'm looking for displacement. I've got my final velocity is 0, so that knocks that whole expression out to 0. I've got 1/2 times 1.5 meters per second squared times 3 seconds squared. So 9, mental math, come on, is equal to 4.5, 13.5 divided by 2, 6.75, I think, meters. So before we box that and walk away, we need to ask ourselves, does this answer make sense? Is this in the realm of possibilities? So 6.75 meters, let's say that's close to like 5 yards on a football field. Could a kid go in 1 Mississippi, 2 Mississippi, 3 Mississippi, 5 meters, 5 meters or 5 yards? Yeah, that's in the realm of possibilities. So that's how you do a problem. We're going to do a couple more, just choosing the right equation, and then you can start working on your worksheet. So these are the steps that I just walked you through. It's how to cook a kinematic equation problem. Okay, so you're welcome to look through that. All right, pause this video and see if you can figure out which kinematic equation to use. And just a quick little reference here to this. Delta x displacement is final minus initial position. So that's where those are coming from. Okay, so we have a displacement, fr. We have a time. She starts from rest, so initial velocity is 0. And how fast is it going to the bottom of the hill? So that's my final velocity. Okay. Now, A looks tempting because I've got that, I'm looking for that, but notice this is average velocity. It sets you up for that one. Can't use that. Velocity is not constant. Okay? So velocity is changing. Stay away from that equation. Even if you have all the stuff that you need, that's only going to give you your average velocity, not your instantaneous. Okay? So looking at the next B, final velocity, we are looking for that. Initial velocity, we have. Acceleration, it says we're experiencing constant acceleration, but we don't know a value for that, so that's unknown. Delta t we do have, so we have two unknowns, so B is out. We have displacement. I've got that initial velocity, I've got that time, got that acceleration. I don't have that time. I have that, but there's one unknown, and that's acceleration. But that's not what I'm solving for, so I'm not going to use that. Displacement, I've got that final velocity. I'm looking for it. Initial velocity, I have it. Time, ooh, that's looking promising. So just to be complete here, final velocity, I'm looking for initial velocity. I have acceleration, I don't have displacement, I have two unknowns, that's out. Okay, so I'm going to use this equation here. Displacement is equal to 1/2 final velocity plus initial velocity. Now, here's something I want you to notice. Notice that I'm using this equation even though it's not equal to what I'm solving for. Okay, that's fine. I can plug in all these values, and then because you know algebra, you can solve for this. Okay, so that's how you do that question. Okay, next question. Pause the video and pick which one you should use. So we've got a time, it's 20 seconds. We've got a displacement. I need to change that to meters, by the way. Starts from rest, so initial velocity is 0. What is the acceleration? Okay, so acceleration is my question mark. So I'm looking for those, an equation with those four things. Velocity is changing, so I can't use A. Initial velocity, final velocity, I don't know and I don't care. So that one's out. Displacement, I have initial velocity, I have time, I have acceleration, I don't have time, I have, oh, that's looking good. That has one unknown, and the one unknown is the one I care about. Displacement, I have final velocity, I don't have initial velocity, I have time, I have. So I've got one unknown, but I don't care about it. Now, here's the thing. You could mathematically solve for this and then use that in another kinematic equation and solve for acceleration and get the right answer. It's just twice as much work. So what I'm going to show you is the more efficient way to do it. So final velocity, we don't know. Initial velocity, acceleration, we don't know. Two unknowns. That's out. So C, I'm going to use that. Okay. I think this is the last one. Pause the video, see if you can figure it out. Okay, you got meters per second, so you need to discern, you got to figure out, hey, is this my initial or my final? You're driving through town, and so this is at the beginning, so our initial velocity is 12. Slow down. Okay, so this is acceleration, meters per second squared. How far did you go before stopping? So this right here, that's your clue, that your final velocity. How far did you go? I'm looking for displacement. Okay. Quick note on this. We're going to say this is the positive direction. The way it's moving, that's just a good suggestion, is make the way it's moving positive. So if we're slowing down in the positive direction, you're going to need to make that a negative 3.5 meters per second squared. You need to you need to give a direction to that. In the previous ones, if it was speeding up, we just kind of is positive, and I didn't really put it in the math. But if it's a negative, that's like when you do the math, that's a thing. All right, so A is out because its velocity is changing. Final velocity, we don't know. Initial velocity, we do. Acceleration, we know. Time, we don't know. Two unknowns. Displacement, we're looking for. Initial velocity, we know. Time, we don't know. acceleration, we know, time. Okay, so we have one unknown of time, but I don't care. So I'm not going to use that one. Displacement, final velocity, I know. Initial velocity, I know. Two unknowns, time I don't know. So final velocity, I know. Initial velocity, I know. Acceleration, I know. Displacement, that's my winner. Okay, so working on that worksheet. It's due on Monday, and hopefully we'll be back in the saddle on Monday. Have a good weekend.